filtering very quickly and focus on two variants, so the batch and the streaming. And I'll then look at the principles of what makes a recommended engine streaming, and I'll talk a bit about some practical issues that you might find and why sometimes you might prefer a batch recommendation engine to a streaming one. So recommender systems are a popular method to match users and ratings, so they define an affinity between them. And in the majority of cases, we assume there's a unique mapping between a user and a product, and that's given by a rating. And in collaborative filtering, the collaborative part comes from the fact that you're using a mass of information about a bunch of users, and the filtering is just another way of saying a prediction. So you're doing predictions based on a bunch of information you have about users and products. So we use collaborative filtering quite frequently in our daily lives, even though you might not think about it like that. And it sounds like common sense. So the main principle about it is, say that you have a group of people which you agree and have similar tastes, then probably in some product that you've never seen, you're going to have the same taste as them. So as an example, let's think about two groups. You have Group A, which is a group of people with which you share a very similar musical taste, and Group B, which is a group of people with which you have a completely different musical taste. So if Group A recommends you an album, which they think is really good, and Group B recommends you another one, so which one would you pick? So I think it's obvious, right? So you'll pick Group A. So this is collaborative filtering, basically, right? But now, if you want, just a bonus question. So if Group B says that an album is really bad, does that mean you like it or not? Exactly. So, you have affinity with one group, you have lots of information, you can say something, but about the other group, you don't have enough information. So it's not very informative. So one of the most popular implementations of recommendation engines and collaborative filtering is alternating with squares, so that's ALS. And in ALS, we assume that you can display the ratings data that you have in a matrix form. So you have users as columns, and you have products as rows. And each entry, in this case, obviously represents a unique rating. So you get a rating that a user gives to a product. And the idea behind alternating with squares is that you factorize this ratings matrix, right? And you factorize it in two factors, U and P. And these are called usually the latent factors. And these latent factors, when multiplied together, they give back an approximation to the original ratings matrix, right? And so to predict a rating in this matrix is simply just multiplying a vector on one latent factor with a vector in another latent factor, being the corresponding user and product in the latent factors. So there are several ways of doing this factorization, and we'll just look at two of them. So that's the batch case and the streaming case. So the factorization is performed by first defining a loss function. So right, you have this loss function defines how do you relate the outcome with the original data that you have. And then you try to minimize this loss function, right? And you have the true ratings in this loss function, which are the ratings for product X and user Y, and the predicted values, the predicted rating for user X and product Y, right? And then you have some normalization factors to prevent overfitting. So you minimize this by taking the derivative of this loss function, you equal it to 0. So you find the solution to that. Unfortunately, this is as a closed form solution, so you can find easily the estimators for this to solve this minimization problem. So the way you do it in alternating with squares is you fix one of these latent factors, you solve the estimator for the other one, right? And then you fix the other latent factor and you solve the other estimator. And then you just alternate this process until you have some error measure, which you see how it's going. And then once it's converging, so once the error measure is really small between two iterations, then you say, well, it's done, this approximation is good enough, so I'll use this. Right, so after you have these latent factors, you can then multiply them back together and you get an approximation to the original ratings matrix, right? And the entries that you were missing are now filled with approximations, right? And these approximations are the predictions. That's what you want. So this, in a nutshell, is how we use ALS to make predictions in a recommender engine. So to illustrate how this works, so let's assume we have a very quirky shop where you have 300 products and 300 users, right? Or 300 customers. And they can give ratings in 8-bit ratings, right? And it's a very weird shop. But now, as we're humans, we see better patterns in colors and in numbers, right? So we're going to assign a color to each of these ratings, right? And I think you know where this is going. So you can just pick like a ratings matrix, which is easy to visualize how it's going to be approximated by ALS. So how do we do this approximation? So first we start by defining random latent factors, right? So when you start with latent factors, you multiply them back together, you're going to get a random ratings matrix, right? But as you iterate, then you're going to get an approximation. I'm sorry, because this is a PDF, I'm going to put the video outside this. Okay, so as you iterate, you're going to get a good approximation to the original ratings matrix, right? And this is quite a simple problem because you have all the ratings, it's a single machine, so it's easy to implement ALS, right? And this is basically how batch ALS works. So back to the presentation. Right. So a fair question is, why can't we use this in a streaming set, right? I mean, we have a new rating. You fill that entry in the matrix, you just calculate the factors, and you have the new approximation. Right, so the problem is that you can use this with streaming incoming data, but to calculate the approximation, you need all the data that you had previously, and that's not ideal in a streaming set, right? So what you want ideally is to have a factorization where you can perform this approximation with just a single new observation, not having access to all the previous ones that you had. And to do that, we're going to look at a method which is based on stochastic gradient descent, and specifically on a specific method called biased stochastic gradient descent. So it is important to keep in mind that from a certain point of view, these two methods do the same thing, right? So they both try to factorize the ratings matrix into two latent factors matrices, but in one, you need all the data, and in the other one, you just need one observation, or 10, or whatever, but you don't need all of them. So in the stochastic gradient descent case, we have this concept of bias. So you have a bias, and the bias of a rating for user X and product Y is given by the bias of product of user X and the bias of product Y plus mu, which is a global average of the ratings, of all the ratings that you have, right? And this bias of X and bias of Y are just how much does it deviate from the other ratings that you have. And this bias information is now incorporated into the prediction, see? So the last term of the prediction is the same as the batch one, but you just add this bias information. And if we take the loss function we defined previously, so we just replace this prediction in that loss function, right? That's the only thing we do, and we do the same steps as previously. So we minimize it, we take the derivatives, we set it to 0, and we can set these new recursions where the bias is calculated based on a previous bias, and the latent vectors are calculated based on the previous latent vectors, right? And you can see from this that we only need one rating, right? So we can update one vector at a time and one bias at a time, just with one observation. We don't need all the other ones. So the practical difference in terms of streaming data is that given both methods, so the objective is to calculate the latent factors, right, given the ratings. But with batch ALS, whenever you get a new observation, you have to calculate both latent factor matrices. And with stochastic gradient descent ALS, given one observation, you just update one row of each latent factor, right? So how does this work? So again, we can see here an example with the same data as previously. So we have random latent factors in the beginning. So I'll just put an animation. Right? And you can see that, well, it's approximating the same, right? As expected, it's converging, but it's converging slower just because now you're taking one observation at a time, right? You're not taking the whole of the ratings that you have, but it's still approximating, but it's going to take longer. But the effect in the end is going to be the same. Now, this works fine for a single machine while implementing streaming ALS, but we're interested in scaling this to something larger, right? So we're going to look at the distributed implementation of ALS, specifically streaming ALS, and this is where things get tricky, right? I mean, as we all know, implementing on a distributed setting has all these new kind of headaches that we never had before. So we'll look at what's going to happen. So back to the presentation. Sorry about that. Right. So I'm guessing most of you are familiar with Apache Spark. And so Apache Spark is an Apache project which aims at, community project, aims at providing a modern distributed computing framework. And Spark provides several core data structures, such as RDDs, which are resilient distributed data sets, data frames, and data sets, right? And the RDD is an immutable distributed typed collection of objects, which is partitioned across different Spark partitions. And then this allows Spark to map operations to partitions that can be executed in parallel, right? So this allows you to achieve high scalability with Spark. And for streaming AOS, we're going to use RDD-based implementation. So Spark provides already AOS implementation on MLlib, but it's a batch one. So it's a batch distributed implementation. And the API is quite simple. So to train a model, all we need is we need ratings. Sorry. So we need an RDD containing ratings. So these elements, this RDD has elements of class rating, which is basically just a tuple wrapping a user ID, product ID, and a rating. And this corresponds to unwrapping the ratings matrix that we had previously. And we need a rank. We need some parameters, extra parameters. We need a rank. So the rank is just going to be the number of columns or the number of rows that you have on each of the latent factors. And on the UNP matrices, as I mentioned previously. And iterations, which is just a number of times the algorithm is going to iterate, as we mentioned previously, right? And the advantage of having iterations instead of a minimum error is that the computations are going to be bound, the time is going to be bound, right? So you can at least expect they're going to stop sometime. And we also have a lambda parameter that, as we saw, is a regularization parameter, which is shown as part of the loss function, the regularization. And since we have the data now, we just need to choose the parameters, right? And so a typical way of choosing the parameters is just splitting the data into two sets. So you have a training set and a validation set. And you train the model with one set, and then you calculate an error measure against the validation, right? And then you choose the parameter which minimizes that error. So it's quite simple to train. So once the model is trained, you get back this instance of a matrix factorization model, which is basically a wrapper around these two RDDs, features, which are basically an integer and array of doubles. And these correspond to rows or columns on the UNP matrices, plus some methods in this class. And we can then make predictions. So it's quite simple to train a model in Spark. But now we want to build a streaming recommender engine. So for this scenario, we're going to assume that we're going to use Spark's discretized streams or D streams. And these streams are basically just consuming mini batches of RDDs over intervals, windowed intervals, right? And we can use, in this case, for instance, the first mini batch to train the model, and we use the next mini batches to continuously train the model. So we initialize it and then continuously train it. And as you can see, one of the immediate advantages is that now we don't need all the observations to update the latent factors, right? So we have a mini batch. They could have 1 or 1,000 observations, doesn't matter. But you don't need the observations from the previous mini batch to train the model. So we'll try to recreate Spark's API. So it's going to be quite simple. Just kind of a train method where you pass an RDD, some parameters, and then you're going to have a method just to update the model given an RDD of ratings. So first we establish the quantities and data structures that we need. So we've seen previously that we need to calculate the user bias and the latent factors, right? So this is just what I've shown previously, but in pseudocode. So this is what we need to calculate in a nutshell. And we create a factor class which wraps the features and their corresponding bias, right? And then if you recall, in the batch implementation, we had RDDs of an integer and an array of doubles, which was the latent factor. But here, it's just going to have an RDD of integers and factors. So we have the bias inside the entry of the RDD. And I'll just do a very quick overview of the steps you need to in terms of RDD operations to calculate, to update the latent factors in a streaming set. So we assume that we have the model data will be in the format of RDDs of ratings, just as in the batch scenario. And we first create an initial user and product latent factors, for the data we just observed. And we do that by creating two separate RDDs, one keyed by user ID, one keyed by product ID, right, and the rating. And the next step is to take each one of those RDDs and create random latent factors, right? So the only thing that we do is we create a vector of size rank, and we fill it with uniform random values, right? And we do the same for the bias. So we have our initial latent factors. Next, we can just join these incoming ratings with the generated user factors and product factors that we had. So we get the resulting RDD that consists of the IDs, the latent factors, right? And for the products and the users. And then we can use this information. Now we have all the information we need to calculate those quantities that you need, right? So, for instance, to calculate the predicted rating, you might remember we just need the biases, the global biases, the individual biases, and the latent factors. So we can calculate the predicted rating easily. So here, a dot function is just a dot product between those two vectors if you consider them as two arrays, if you consider them as vectors. And we have the error, right? So it's straightforward to calculate because we have the rating on the RDD. We've just calculated the prediction. And now we can, we know that gamma and lambda are parameters that we gave to the model, right? So we can calculate the gradients for the latent vectors, right? So we can calculate all the quantities that we need. So we update everything given the previous bias. So as you remember, the recursion we have for the bias and the user vectors. So we calculated the gradients. Now we can map them to new RDDs where we can just have the final biases and the latent factors just in one RDD. Each entry contains both. And the last step, we just split the gradients according to user and product, right? So you're going to have lots of entries for each user and each product, but we just want one. Remember, we want a vector for each one. So what we do is we just perform an aggregated sum. So we just reduce the whole thing using an aggregated sum, and we have the final quantities that we need. So these steps define entirely the streaming ALS operation, and for each observation now we can calculate and update the model, right? So we've covered the initialization case. And for the other cases, it's quite simple. So if you have observations that we haven't seen before, right, they're here in red. That we haven't seen before, and the black ones is the ones we've seen before. What we do is just we do a full outer join, right? And now we use the latent factors that we had for the previous entries that we have ratings. And for the ones that we don't have ratings, we just recalculate as previously the latent factors, right? Starting from scratch. So making random values for the initial latent factors. And we just repeat the process as previously. So it's quite straightforward. So to test this, we use the movie lens data. I'm a bit pressed for time, so I'm just going to skip that. So it's quite a common data set in recommendation engine research. We use the full one with 26 million ratings. And we just train the batch ALS as standard in Spark. So nothing new here. We looked at this. And we trained this also with streaming ALS. So in this case, we just took out the validation we use, the ratings we use for the batch ALS, and the remaining ones we turn into a simulated Kafka stream, and we use that Kafka stream to train the streaming ALS. And we calculated the error measure for both of them. So as you can see from here, so the dashed line is the baseline, so that's the batch ALS root mean squared error for this data set, and the blue one is the actual streaming implementation. So you can see, it's jiggling about, but it's actually converging to, as the observations trickle in each batch, so each slice is a mini batch of 1,000 observations, you can see it's actually converging to the batch ALS value. So some things to consider when using streaming recommendation engines, because not everything is rosy or not everything is that good, is that you still suffer from this cold start problem, as in batch ALS. That means that if you have too few observations, your recommendations are going to be meaningless. And that's true for both of them, but the fact is if you're using a streaming recommendation engine that you can use in real time, you probably feel tempted to start giving predictions right away, and that's going to be, you might consider that. So you either do some diagnostics on your predictions, or you train it offline before you start serving predictions. And another thing is that in batch ALS, it's quite simple to train a model. So we have this set of parameters, right? You calculate the error measures, and then you choose the parameters that minimize the error measures. Now, in streaming ALS, that's not straightforward because you have a new batch of observations, and you discard the previous observations. So if you want to retrain the model with new parameters, you're going to have to pick all the previous observations. And if you're going to use all the observations that you had, you might as well use batch ALS. So, right, the whole point is that you just use the streaming observations. And a solution to this is probably to have like a bunch of models in parallel, right? You train them in the beginning, and then you start pruning the models as time goes by if they don't perform very well, right? But the problem is that this is very computationally intensive, and it does just because, like, say, model A you decide is not very good, just because a model is not very good in the beginning with very few observations, it doesn't mean it's the worst one. It might actually be the best one. You don't know. You just have to. You don't have too much information on it. So just two final considerations. We use lots of joins, as you see, operations in this implementation. So it's advised to have like a good partitioning strategy when implementing this type of algorithms. Otherwise, it's not going to be very performant. Spark's ALS is quite good in this. So they have this blocked implementation where they calculate in links and out links. So they know which vectors match more with each product and user, so they can block the whole thing in one partition to minimize network communication. So this is a kind of naive implementation in that sense. And another thing is that to make predictions, after you train a model, you need to have some kind of random access to the RDD vectors, right? So if you want to calculate predictions for a certain user and product, you have to get those vectors. And RDDs don't really allow for random access, so you have to perform some kind of lookup, and that can be also a bit expensive. And that concludes my talk. Thank you very much. And if you have any questions, please let me know. Oh, so there was one question, yeah?
Do you have a system for tracking those models?
For tracking the models.
Somebody said model 1 will be good when you have different sets growing.
Yeah. Yeah.